Hello everyone, in this video I'll be explaining the chemical properties of alkenes. Now, we know that alkenes are the unsaturated hydrocarbons with at least one double bond. Now, alkenes, they have a rich source of loosely bonded pi electrons in them because if we consider here the carbon-to-carbon double bond, the pi electrons are loosely bonded. Therefore, the alkenes, they are attacked by electrophilic reagents. For example, this is a typical alkene molecule, and if this is a reagent here, now one attacks here and then the other attacks here to get our A and B here, to get our product in this way alkanes are formed. Therefore, let's check out some of the chemical reactions of alkenes. The first one is halogenation reaction. Now, what is halogenation reaction? Now, halogenation reaction means the addition of hydrogen halide across the carbon-to-carbon double bond of the alkene. Means one hydrogen and halogen atom is added to the carbon-to-carbon double bond, which makes us clear that there will be breakage of one of the pi bonds, and then the hydrogen and the halogen atom would be attached in the alkene molecule to form the product of this kind. So let's check the reaction. An alkene. Now, hydrogen halides. Hydrogen halides are the reagents. Now we know that since the bond is polar, this will be partially positive and this will become partially negative. Now, in this here, our hydrogen halide, it produces a proton. H plus is released as a proton, and this H plus acts as the electrophile, and then it attacks here, and then the negative part it attacks the second carbon. Therefore, since there is breakage of one bond, the hydrogen would be attached here, and then our halogen would be attached here. Therefore, this would be known as alkyl halides would be formed in this case. Now, symmetrical alkanes. For symmetrical alkanes that is of this kind, after the number of carbon atoms it's the same on both sides, means that they are symmetrical alkanes. Now, when it reacts with hydrogen halides, the H plus attacks one carbon, the halogen attacks the other carbon, and then we'd be getting CH3, one bond breaks, CH2, and then Cl. So this is our two carbon atom, therefore ethyl chloride. This is our ethyl chloride molecule. However, in the case of unsymmetrical alkenes, what would be the cause? Here, in the case of unsymmetrical alkenes, Markovnikov's rule is followed. That is, the proton, that is the hydrogen atom, attaches with the carbon atom having more number, or having the majority of hydrogen atoms. Therefore, let's check out the reaction here. CH3 CH double bond CH2. Now, this is an unsymmetrical alkene because the number of carbon atoms on the opposite sides are different. Now, when a hydrogen halide attacks here, okay, now in the first case, if our hydrogen halides, now since there should be breakage of one bond should break here. Now, if our hydrogen halide attacks in such a way that it attacks this carbon atom, now what would be the case here? Now, our case here would be, let's check out here, CH3. Now, this bond breaks up, and then the whole thing comes to this carbon atom. Therefore, we'll be getting here CH double bond, single bond CH3, and then this would become, since the double bond broke up and then the 2 bonding electron went to this carbon atom, we'll be getting a positive sign here. Now, this is a secondary Now this is a secondary carbocation. Now we know that stability of carbocations are the tertiary carbocation is more stable than secondary than primary carbon atoms. Now keeping this in mind, we know when the bond breaks up here, you'll be getting a secondary carbocation here. Now however, if the reverse takes place, like if this bond were to break and it's just similar, if one bond breaks and then along with the two bonding electrons it moves here, then we'd be getting here CH2 and then CH2. This would remain the same, one note, and then these are the positive sign would appear here. And now this is as primary carbocation. Now we know that comparing the primary cation and secondary carbocation, if we compare the stability, we know that the secondary carbocations are more stable than the primary carbocations. Therefore, the reaction would proceed in this way, and this reaction would not be accepted. Now, here, the reaction comes here now. Our halogen halide comes here. The X minus is here. Now, what is our X minus? Now, halogen halide CH3 CH X minus comes and attaches to this carbon atom, therefore X, and then CH3. Now this is the product. Therefore now the Markovnikov's rule occurs in such a way that the hydrogen, the proton H plus, attaches to the carbon atom having more number of hydrogen atoms. Therefore now if we consider this atom, now this carbon and this carbon, now which is having the more number of carbon atoms, therefore we see here that this carbon atom is having more number of carbon atoms, therefore the H plus would come and attack in this carbon atom, therefore the CH2 became the CH3. I'm showing here a short trick for this reaction, and then CH3, and then the halogen would attach to the carbon atom with the least number of hydrogen atoms. Therefore our product is obtained in this way when unsymmetrical alkenes undergo hydrohalogenation reaction. Now let's check some more reactions of this chemical reaction. Now let's check another example, unsymmetrical alkenes. CH3 C double bond CH, and then CH3 and CH3. Now this is an unsymmetrical alkene. Now when hydrogen HCl, okay, let's take hydrogen halides, this will be R plus, this will be R minus. Hydrogen halides the H plus, the electrophile attacks the carbon according to Markovnikov's rule. The H plus attacks the carbon atom having the more number of hydrogen atoms. Now if we consider this, we'll be considering this carbon and this carbon. Now this carbon has more number of hydrogen atoms as this. There is no carbon hydrogen atoms here, whereas for this carbon we have one hydrogen atom. Therefore the H plus would attack here, and then the Cl minus would come and attack here. Therefore the product here will be CH3 C single bond CH2, one hydrogen came and attack. Our Cl would be here CH3 and then CH3. Therefore this is our product for this reaction. Now for the reaction of these hydrogen halides, the order of the reactivity of the hydrogen halides is H hydrogen iodide is more reactive than hydrogen bromide than hydrogen chloride. Now why is it so? Because if we consider the bond length of hydrogen iodide is longer as compared to, therefore it takes less energy. The bond length is long, therefore since the bond length is very long, it is very easy to break, and therefore the reactivity of hydrogen iodide is more as compared to hydrogen bromide and hydrogen chloride. However, hydrogen fluoride is not taken because the bond energy is very high. Because of short bond length, we need more energy to break the bond, therefore this is not required in the process, and only these three hydrogen halides undergo hydrohalogenation reaction for the chemical reactions of alkenes. Now let's check one more example here. This is an important example, CH3. This example I've done in the first page, that is CH3 CH double bond CH2. Now when it breaks with HBr, now what was our product here? According to Markovnikov's rule, the electrophile should attach to the carbon atom having more number of hydrogen atoms. Therefore, our H plus would come and Br minus Br would come and attach here. Therefore, CH3 CH our Br would be here. Single bond will, because one bond will break, and then this would become C here. This is 2 bromo propane. This is our major product, and this will be our product because we know that in Markovnikov's rule, I'm repeating it again, the electrophile attacks the carbon atom having more number of hydrogen atoms. Now, let's check what is anti-Markovnikov's rule. Anti-Markovnikov's rule. Now, what is anti-Markovnikov's rule? Anti-Markovnikov's rule is just the reverse of Markovnikov's rule, or it is also known as the peroxide effect, or Karash, or the Karash rule. Now, what is this rule? In this rule, if we take an example here, since it is the reverse, HBr reacts, it is the reverse in the presence of peroxide, that is H2O2. Now, the hydrogen, since it is the reverse of Markovnikov's rule, the H plus R electrophile would attack the carbon atom having least number of hydrogen atoms. Now, if we consider this is the alkene group, so hydrogen atom would attack the carbon atom with the least number of hydrogen atoms, and then our Br minus would come and attack this carbon. Therefore, our product here will be CH3C. We have our CH3, the H would come and attack here, and then CH2, and then Br. Now, this anti-Markovnikov's rule has some conditions, because the condition is that anti-Markovnikov's rule is applicable only to the hydrogen halides, that is only for HBr, and here free radical mechanism occurs. Free radical mechanism occurs, that is in the presence of sunlight. Now, in Markovnikov's rule, carbocation was formed, but however, in anti-Markovnikov's rule, free radical mechanism, free radicals would be formed, and then the condition is only the hydrogen halides, that is HBr, would undergo the anti-Markovnikov's rule, and hydrogen peroxide is used as the reagent for anti-Markovnikov's rule. There are 5 more chemical reactions of alkenes. Therefore, I will be explaining one by one in separate videos for all the chemical reactions.